Hey Chem Kids, Campbell here. In this video, we're going to learn how to do calculations for weak acids. So if you remember in the second video, we talked about the difference between strong acids and bases and weak acids and bases. And it was about how much they ionize in solution, so how much they come apart. And strong acids and bases completely come apart. So we can just do the whole negative log of the hydrogen ion concentration to get a pH. But we can't do that for weak acids because they only partially ionize. So they only have some of their hydrogen ions come off in solution. So we're going to learn how to do those calculations, and guess what? It's going to involve that K thing again. Yeah, remember last unit, the KEQ? Yeah, we're doing those, but now we're going to call them Ka for acids. So if you remember about KEQ, it's about the ratio of the products to the reactants. And so remember, you put like the products on top divided by the reactants on bottom, and the concentration raised to the power of the coefficients. And basically that tells you how much is in solution. And so for us, that's going to tell us how much hydrogen ion is in solution. So remember how to calculate K? Well, here is a reaction equation for an acid. I just made up this acid. I just called it HA. So HA dissolves into hydrogen ions and A, the anion, in solution. And so when we write our Ka, which is just like KEQ, right, we do brackets over each of the products on the top. And in the denominator, we have brackets around our reactant, which is our HA. And you'll notice that there are no powers here. There's no coefficients because my made-up acid is balanced. This equation is balanced right now. So Ka is called the acid dissociation constant. And the higher a Ka, the stronger the acid, right? Because that means I have more product, which is the hydrogen ion in solution. So if I have a Ka greater than 1 or a Ka less than 1, which would be the stronger acid? Well, that would be the one that's greater than 1. In fact, here is a list of some strong acids and weak acids. Actually, I take that back. They're all weak acids. Take a look at the Ka values. Which one is the strongest acid and which one is the weakest acid? Well, if you said number 2 was the strongest, you're correct, right? Because that number, 1.2 times 10 to the negative second, is the biggest number we have. The weakest one is the carbonic acid. That's what's in your soda. Yes, there's acid in your soda. Bad for your teeth. So that one is our lowest Ka, so it's our weakest acid. All right, so let's calculate Ka. So the first thing you're going to have to do is you're going to have to write the equation. For KEQ, I gave you the equation. Now you're going to have to write it. Second step is you're going to write the K expression, our Ka expression, from that equation. Then you're just going to plug in the values that are given. And if there is something you're not given, you're going to put an X in it. And then you're just going to do the algebra. Now, sometimes you're going to get a question that also asks for the pH. So when you are solving for hydrogen ion concentration in some of these problems, right, that's what you do the negative log of to get the pH. So we'll do one of those as well. So let's take our made up acid, HA, and let's do this. A solution of HA has an equilibrium concentration of 1 molar. At equilibrium, the hydrogen ion concentration and the A concentration are 0.2 molar. What is the Ka value? All right, so step 1, write the equation. All right, so we're going to take our HA. We're going to make our double arrows. Weak acid means that it's a reversible reaction, and that produces H plus A minus. Now, if you don't put the pluses and the minuses up there, that's fine. It's not super important to the calculation of Ka. Then we're going to write our Ka expression. So we're going to put brackets around our H plus and brackets around our A minus. Remember, these are multiplied together, so don't put a plus in between them. And then on the bottom is our HA. All right, now all we got to do is plug in our numbers and do some math. So we're solving for Ka. The H and the A minus concentrations are both 0.2. So we're going to do 0.2 multiplied by 0.2. And then we're going to divide that by 1. So HA has a concentration of 1. So all we got to do is multiply 0.2 times 0.2, divide by 1, and we get a Ka value of 0.04. So similar, right, to what we did in our last unit. All right, how about we take a real acid? Here is acetic acid, aka vinegar. And let's write the reaction equation first. So all you have to do when you write a reaction equation is you just take the H off of it. So here is our reactant, HC2H3O2, right? That's acetate 232CHO. And we make our little double arrows and we pull off the H, and then we just write the acetate. The acetate doesn't come apart. Polyatomic ions do not come apart. Then we write our Ka expression. So Ka would be brackets around the H and multiplied by brackets around the acetate ion, all over our reactant, which is our acetic acid, HC2H3O2. All right, if I go back and I look at the numbers, it says that I have a 2 molar solution of the acetic acid, and I have a Ka value. But what they want me to find out is what is the concentration of the hydrogen ion. Now, if you look, we have, when this breaks apart, we have one H and we have one acetate. So that means they actually have the same concentration. So we're going to just call both of these guys X's. We're just going to put little X's in. So when I write this, I'm going to put this in for my Ka, the 1.74 times 10 to the negative fifth. That's equal to, so since I am trying to find H, we're going to call that an X. We're also going to call the acetate ion an X because we don't know what that is, but it's going to be the same as our hydrogen ion concentration because it's just one of each. And then on the bottom, we put the 2. So we just got to do some math here. So we multiply both sides by 2. And what happens when you multiply X times X? You get X squared. So X squared is equal to, and 2 times 1.74 times 10 to the negative fifth would be 3.48 times 10 to the negative fifth. And then we just got to solve for X. So we got to take a square root. And the square root of that is 0.006. And that's concentration, so that's big M. So that's my concentration of hydrogen ion. So I'm not done though, because it wants me to know wants to know the concentration of hydrogen ion, and it also wants to know the pH. So how do I get pH again? Well, I got to take the negative log of the hydrogen ion concentration, which is just your value of X. So that's negative log of 0.006. And when you plug that into your calculator, you should get 2.23. So that's our pH. It's very acidic, even though it's just a weak acid. All right, how about you try this? We have hydrofluoric acid. It has a Ka value of 1.3 times 10 to the negative ninth. Find the hydrogen ion concentration and the pH if the concentration of the acid is 0.35 molar. Pause the video, see if you can work through this. The answers are at the bottom of the screen. So you should have written your reaction equation. So HF, double arrow, and then just break them apart. We get one H and one F. We write our Ka expression, brackets H times brackets F, all over our reactant, which is HF. Just plug in your numbers, and for the H and for the F, we're just going to put X's. So the Ka we're given, that's our 1.3 times 10 to the negative ninth. That's equal to X times X, or you could just write X squared, divided by the concentration of the acid, which is 0.35. Now, you just do the math, right? When you do the math, you should get that X is equal to 2.13 times 10 to the negative fifth. And then remember, to get the pH, you just take the negative log of the value of your X. So you just take negative log of 2.13 times 10 to the negative fifth, and you should get a pH of 4.6. How'd you do? Try some of the problems in your packet, and if you have questions, let me know.